The Java memory model is the core specification that defines precisely how and when different threads can reliably see values returned to shared variables by other threads, and exactly how to synchronize access to those shared variables when necessary. Sounds intense, right? Don't worry, it will all make sense once we walk through it. To fully grasp the Java memory model, we need to understand the two primary memory areas in Java Virtual Machine: the thread stack and the heap. When new Java thread is started, a dedicated thread stack is created for it. This stack stores information about the methods that have been called, as well as any local variables declared within those methods. So if two different threads call the same function, a counter and flag variable are stored in each thread's private thread stack. Stack data is strictly private to its own thread. No other thread can directly access another thread's stack. All local variables of primitive types like boolean, int, long, double, etc. are stored entirely on the thread stack. A local variable, however, may also be a reference to an object. In that specific case, the reference, which is the local variable itself, is stored on the thread stack, but the actual object instance it points to is stored on the heap. The heap is the memory area where all Java objects reside. The critical difference here is that the heap is shared by all the threads running within the application. Because heap is shared resource, any object stored here can be accessed and potentially modified by multiple threads, which immediately leads to the concurrency issue. It does not matter if an object was created and assigned to local reference variable. The object instance will still be stored on the shared heap, while its reference remains on the thread stack. Wrapper class objects like byte, integer, long are also stored on the heap. An object's member variable or instance variable are also stored on the heap right alongside the object itself. This is true whether the member variable is a primitive type or a reference to another object. The string pool is also a key area stored within the heap, and garbage collection primarily operates on the heap memory to reclaim the space. Let's look at a simple example with some local variables: message, counter, and ID. Since counter is a primitive type int, its value is stored directly on a thread stack. The references for message pointing to hello string and ID pointing to integer instance are stored on a thread stack. However, the actual objects they point to, the hello string and the integer instance, are stored on the heap. Now consider a member variable, like name defined in this class. That name is an instance variable, so it is stored on the heap along with the rest of the class objects data. To summarize, all local variables of primitive types and references are stored on thread stack, and all objects, member variables, string literals are stored on the heap. Both the thread stack and the heap are located in main memory. Parts of the thread stack and heap may sometimes be present in the CPU cache and in internal CPU registers during operation execution. So the core problem here is thread 1 and thread 2 have their own isolated stacks, but they share the exact same heap. If thread 1 changes a shared object that resides in a heap, thread 2 might not see that change immediately due to CPU caching mechanism. This is exactly what we observed in our previous demo, where the main thread updated the stop variable to true, but the worker thread continued reading the stale data false value from its own local CPU cache. Understanding this memory segmentation is the first step to writing reliable concurrent Java code. Here are the two main concurrency bugs we have observed so far. Race condition. We touched on this in the introduction video, but here is the concrete example. Thread 1 reads the share variable ID into its CPU cache. At the same time, thread 2 does the same into different CPU cache. Both threads increment ID by 1. Each cache now holds an incremented value, so ID has effectively been incremented twice, once in each cache. If those increments had happened sequentially, the value in main memory would be 2. But because they happened concurrently without proper synchronization, whichever thread writes back its value last will overwrite the other, and the value in the main memory will end up as 1 despite 2 increments. Now let's move to the second problem, visibility of thread updates to shared variables. Imagine a shared variable stored on a main memory. A thread running on CPU 1 reads that into CPU cache and modifies it there until the CPU cache is flushed back to main memory. That updated version is not visible to thread running on other CPUs. As a result, each thread can end up working with its own copy of same object, with each copy sitting in different CPU cache. To summarize, lack of visibility and missing synchronization can cause threads to work with stale or conflicting copies of shared data, producing incorrect results even for simple operations like incrementing a counter. So how do we fix these problems? First, let's tackle the race condition. To solve this, you can use Java synchronized block. A synchronized block guarantees that only one thread can enter a given critical section at a time. It also ensures visibility. Variables read inside the synchronized block are loaded from main memory, and when the thread exits the block, any updated variables are flushed back to main memory. Now let's look at the key parts of synchronized approach. Synchronized block. This acquires a monitor lock associated with ID lock object before entering the block and releases it when the block exits. While one thread holds the lock, no other thread can enter any synchronized block that locks on the same object. For finer control and better encapsulation, prefer a private lock object instead of locking on current class object. If block. This checks whether ID is null. If it is, the code initializes ID to 1 and returns. Because this check and initialization happen inside the synchronized block, the operation is atomic with respect to other threads that synchronize on the same lock. ID++. This increments ID. Placing the increment inside the synchronized block protects the read modify write sequence from concurrent interleaving by other threads that use same lock, preventing lost updates. In short, synchronized block enforces mutual exclusion and establishes the necessary visibility guarantees so that changes made by one thread become visible to other threads that later acquire the same log. So let's run this code and simulate 100 users triggering it simultaneously using Apache JMeter. After running the test plan, we don't have any duplicates. And we have exactly 100 IDs. Is this the only way to fix race condition? Absolutely not. You have other options. Synchronized method. Simpler to write, it locks the entire method on this, that is current object, or on the class for static methods. Use it for quick instance level critical sections when you don't need fine grained control. Atomic classes for single variable atomic operations. Classes like atomic integer or atomic reference provide lock-free atomic operations. For example, increment and get, and compare and set, and avoid taking Java monitor lock. Now, when to use which? Use a synchronized block when you must protect multiple fields or group several operations into one atomic critical section. Prefer private final lock object to avoid external interference. Use synchronized method for short, simple critical sections where method level locking is acceptable. Use atomic types for counters, flags, or single variable state where you only need atomic read, modify, and write operations. We'll discuss about atomic classes in much more detail in later videos. Now let's fix the second problem, visibility of thread updates to shared variable. To address this, use Java's volatile keyword. Declaring a field volatile ensures that reads always come directly from main memory and writes are immediately flushed back to main memory. In other words, volatile variable cannot be cached in a CPU core local cache in a way that hides updates from other threads. First, I'll run this code as it is to show the problem in action. So stop variable is not a volatile variable here. Program runs indefinitely because the worker thread never sees the update made by the main thread. Watch how worker thread keeps running even after main thread changes the stop flag to true. Now I'll make stop variable volatile and run the program again. And here is the difference. The program no longer runs indefinitely. After making the stop variable volatile, the worker thread observes the update from the main thread and stops after a while. That's the effect of volatile. It provides the visibility guarantee that simple shared flags need. Use volatile for simple shared flags or single variable visibility requirements. For more complex coordination or compound actions, prefer synchronization, either synchronized block or synchronized method. Higher level concurrency utilities from Java utility concurrent package. So far, we talked about memory visibility. Now let's move on to understand what compiler and CPU optimizations are and what happens before relationship is. Let me start by explaining something that might surprise you. The code you write isn't always executed in the exact order you wrote it. Modern processors and compilers are constantly looking for ways to make your code run faster. And one of their favorite tricks is called instruction reordering. Think of it like this. When you have independent operations that don't rely on each other's results, the system can rearrange them to keep the processor busy. For example, your original code calculating total, then setting customer name and updating is verified to true, but the system might execute it like this: setting the customer name, then updating the flag, then calculating the total. This reordering is completely safe in single threaded programs because the end result is the same. The problem only appears when multiple threads get involved. Let me show you a real example of how this can go wrong. Imagine we have a simple configuration loader that two threads might use. What could go wrong due to reordering, you may ask? Thread 1 might actually set config ready equal to true before setting database URL. Thread 2 sees config ready equal to true and tries to use database URL, but it's still null. Your program crashes with null pointer exception. This happens because two assignments, database URL and config ready, are independent from processor's perspective. So it feels free to rearrange them. So here comes the happens before guarantee to rescue. The happens before guarantee is essentially Java's promise about when one thread will see another thread's change. It's not about the exact order things happen in time, but about what changes are visible when. Now let's see how the volatile keyword gives us two important guarantees. Visibility on write. When you write to volatile variable, two things happen. The new value is immediately written to main memory and not just to processor's cache. And all variables that were visible to the thread also get flushed to main memory. Visibility on read. When you read a volatile variable, the value is freshly read from main memory and all other variables visible to the threads are also refreshed from main memory. But wait, what if the instructions still get reordered? This is where happens before guarantee comes in. For volatile writes, happens before guarantee is any writes that comes before volatile write in your code must actually happen before that volatile write. The system cannot reorder them to happen after. In our example, database URL must happen before config ready. The system cannot rearrange these so that config ready gets set first. For volatile read, happens before guarantee is any read that comes after volatile read must actually happen after that volatile read. This read refreshes database URL too, and this established connection is now safe. The system cannot rearrange these, so the database URL gets read first before checking config ready. Synchronized blocks provide similar guarantees through a different mechanism. When entering a synchronized block, the thread refreshes all variables from main memory. It's like getting a fresh snapshot of everything. When exiting a synchronized block, the thread flushes all modified variables back to main memory. It's like saving all your changes. Let me show you with the bank account example. Block entry guarantee is no reads can be done before entering a synchronized block. This ensures you see the most recent value assigned to balance variable. Block exit guarantee. No writes can be done after exiting a synchronized block. This ensures your changes to balance variable are visible to other threads. The happen before guarantee is what makes writing reliable multi-threaded code possible in Java. Without it, we would be left guessing when or if our threads would see each other's changes. Before ending this video, I would like to talk about two more important points. CPU cache coherency. When we talk about variables being flushed to memory, what really happens is more nuanced. Here is the actual process. When a thread needs to make its changes visible to other threads, the CPU doesn't necessarily write everything all the way to main RAM. Instead, here is what typically occurs. Variables stored in CPU registers get written to CPU's cache, L1, L2 or L3 cache. The hardware uses cache coherence protocol, a sophisticated method to ensure all CPU caches can see each other's changes. Main memory is optional. The data might later reach main memory if it stays in cache hierarchy. The key insight is that from programmer's perspective, it does not matter whether the data actually reaches main memory. What matters is that when another CPU requests that memory address, it gets the most recent value, whether that value comes from another CPU's cache or from main RAM. The hardware handles all this transparency through cache coherence protocol. While there is a performance cost to maintaining cache coherence, it's much more efficient than writing everything to main memory and reading it back. Now imagine two threads running on different CPU cores, each working with their own variable. If these two variables happen to be located in same CPU cache line, you can get false sharing. The cache line is the basic unit of data transfer between CPU caches and memory, typically of 64 bytes. When a CPU reads or writes data, it operates on entire cache lines and not an individual bytes. So how false sharing occurs? Thread A on CPU 1 modifies variable X. Thread B on CPU 2 modifies variable Y. Both variables happens to be in the same 64 byte cache line. When CPU 1 modifies X, it marks the entire cache line as dirty. CPU 2's copy of that cache line becomes invalidated. When CPU 2 needs to modify Y, it must first reload the entire cache line. This creates unnecessary cache synchronization traffic. The problem is that the threads aren't actually sharing the data. They are working with completely independent variables, but because those variables are physically close in memory within same cache line, the hardware treats them as shared. For most applications, the impact is negligible, but for performance critical code like financial trading systems, scientific computing, or high frequency data processing, addressing fault sharing can provide significant performance improvements. Understanding these low level details help you write more efficient concurrent code and diagnose performance issues that don't show up in standard debugging. Wow, what a journey we have been on. We started with a simple piece of code that had a hidden bug, the worker thread that never stopped, and we dove deep into the reasons why. We explored the intricate world of CPU caches and the Java memory model, and the crucial concept of the happens before relationship. We learned that in multi-threaded environment, what you see in your code isn't always what you get at runtime. The CPU and compiler optimizations can rearrange instructions, and the caching of variables can lead to visibility issues and race condition. But we also learned how to tackle these problems. Use synchronized for atomicity and visibility when dealing with compound actions. Use volatile for visibility of single variables and to prevent instruction reordering around that variable. And we even touched on the hardware level, understanding how cache coherency and fault sharing can impact performance. Remember, concurrency isn't magic, it's a discipline. By understanding these fundamental concepts, you are now equipped to write more reliable, efficient, and correct multi-threaded code. So the next time you are writing code that uses multiple threads, I encourage you to pause and think, are my shared variables properly synchronized? Am I using the right tool for the job, whether it is synchronized, volatile, or atomic classes? And if you are in high performance scenario, consider the layout of your data in memory to avoid false sharing. Thank you so much for your attention, and may your threads always be safe and your performance always be optimal. If you found this video helpful, please give it a thumbs up and subscribe for more technical content.